We're going to take you through a demo scan of our system. We're currently in the initial state of our app, but we'll take you to our developer options where we can change the variables of the microcontroller. Here, we're changing the goal temperature, and we're setting this to 32 degrees Celsius. Here's our acknowledgement back. Now what we do is we click Start Scan. From here, we insert the blood chip. Then what we do is we insert the blood, put that onto the chip, and then we cover it. Afterwards, we click Start Scan. Here, our status information turns green to show us where we're at. Then, the current temperature approaches the goal temperature. Once the current temperature is within 0.3 degrees Celsius of the goal temperature for more than a couple seconds, this starts the M-step pico scanning process that's happening right now. Now the results are ready from the pico. We now click this button, and the results are now displayed on this screen. This data now feeds into Aptitude's coagulopathy measurement engine.
Hello everyone, we are RTCM, Real-Time Coagulopathy Measurement, and we are sponsored by Aptitude Medical Systems, Inc. Here's our development team. I'm Justin Hemphill.
I'm Trenton Rochelle.
I'm Ziming Qi.
And we are help making the next life-saving product. So just a quick overview of what we're dealing with. Coagulopathy of trauma. It's a state someone goes into when they've suffered a traumatic injury, such as a car accident, a shooting, or a bad fall. It's a hypocoagulable state, resulting in increased bleeding or clotting, heightened resuscitation requirements, and a 4 times increased rate of mortality. It's very important to monitor this state of a person nearest to the time of injury and also monitored throughout the course of care. So there are current solutions to monitor coagulopathy, but these measurements can only be taken in a hospital or lab setting, and they can take up to an hour. This isn't great when seconds matter when treating a critically injured person. So Aptitude, our sponsor, has created a solution. They created a proprietary molecule that binds to receptors in a person's blood. The electrochemical signals produced by the molecular binding provide the coagulopathy measurement. They did this on a handheld sensor that's analogous to a blood glucose meter used by diabetics. And they've gotten the test down to about 30 seconds. A quick overview, recap of what I just said. Current solutions to measure coagulopathy can only be done in hospital lab or labs. They take up to an hour. They use stationary, often large machines, and are used by doctors and lab technicians. Aptitude solution, however, is portable, is guaranteed to be done in less than 2 minutes, is handheld, and can be used by first responders. So at the beginning of the year, Aptitude gave us their alpha prototype. It's basically just a phone, an Android phone in a case with something on the bottom, a chip, a blood chip that can be inserted. And the process here for inserting the blood is shown over here on the right. There's the chip, and you drop some blood on it. It goes through the capillaries of the chip as pictured down below. And then once the blood has gone through the chip, the measurement can be taken. So the alpha prototype was pretty remedial. So we wanted to design a new system. Some of the main product requirements of this system is that it has to be handheld and field ready during an emergency. Also, the blood within the sensor needs to be at a stable temperature for various goal temperatures. We gave Aptitude the flexibility with our final design to heat or cool anywhere between 15 and 60 degrees Celsius. This is useful for Aptitude because they are not exactly sure where the best temperature is for their test. So some of the goals of our system were to design a temperature control system. This is important because the device needs to work in any environment, in a desert or in the blistering cold. Wanted to integrate all the modules into a PCB for a small form factor, provide feature expandability, have the device charge while in use, redesign the enclosure, and of course keep in mind that we need quick and reliable readings. Some of the design limitations imposed by Aptitude were no Bluetooth, due to the possibility of the device being used in military applications. We of course wanted long battery life, it to be handheld, work while charging, and work with Android. So we created a system. Here is the simplified block diagram of our system. The user uses an Android phone to control the system. The microcontroller, the slave, communicates between all of the other subsystems in our entire system. We have a blood reading system up here, a temperature control system, and of course, a power system. So we needed to choose some core modules to make this system. We started with our central processor. We chose a SAMD21 Cortex. We did this because it was low power and it did all of the communication interfaces that we needed. We actually utilized SPI, UART, USB, general purpose input and output, and PWM waveforms. Then we needed an MStat Pico. This is really a really important device for the blood reading part of our system. It's a highly compact potentiostat used for taking the electrochemical measurements and thereby providing the actual coagulopathy measurement. Our power system is pretty simple. It's just a LiPo rechargeable battery, 3.7 volts, 2,500 milliamps, pretty small guy, not too thick. And we needed a battery controller to charge the LiPo safely, because if you just charge up a LiPo, it'll just catch on fire. So you need a specialized circuit, something like this down below. This battery controller also gives us some battery level readings, it boosts our output, and allows us to charge and use the battery simultaneously. Then we went on to create our temperature control system. We needed a module that could both heat and cool the blood in the blood chip. So we chose this Peltier device pictured on the right. It's basically two ceramic plates connected through PN junctions. And when given an electrical current, one plate will draw heat from the other plate. So one plate gets hot, one plate gets cold. So the coolest thing about this is that if you switch the electrical current, if you switch the direction of the current, the same side that was once getting hot will now get cold. So we can use the same side for both heating and cooling. Also, it's a pretty hungry device. It runs at 9 volts at 800 milliamps. Of course, we needed to figure out what temperature we're at while we're heating or cooling up the blood chip. So we decided to mount a thin film thermistor onto the Peltier. You can see it's pretty thin by this diagram or this picture on the bottom. Then we attached a digital amplifier to it that has a 0.02 degrees Celsius resolution, which is very accurate. And we're reading the temperature about every 100 milliseconds.
Okay, so now that we have that all set up, we need to be able to control the Peltier. And we're doing this through a simple input-output. We want to be able to input the current temperature reading from the digital amplifier. And then we want to output a PWM duty cycle such that we can control the H bridge and limit the current going through the device. To do this, we're using two PID controlling objects. We're using one for heating and another for cooling because they have different tuning parameters, which I'll go over. So PID stands for proportional integral derivative, and this is a control loop mechanism that employs feedback. We are continuously calculating the error value as the difference between the desired set point YT, which in our case is the goal temperature, and the measured process variable RT, which is our current variable, our current temperature. This applies a correction based on the proportional integral and derivative terms. We look at these terms, scale them, sum them back up, and this output then goes back into the system where we then look at the current temperature again, and the error value is then calculated again. This process repeats. So PID tuning is a little precarious. So here we have an animated plot of amplitude over time. As you can see, as the PID terms, as the scaling becomes as the scaling terms become more accurate and towards the system and what it needs for a quick response, we get there in a short amount of time, it becomes stable, and we reduce oscillations. Here are our results with initial heating tests with no enclosure. When we use the scaling terms 5, 3, and 2 for the PID, we can get from 25 degrees Celsius to 37 degrees Celsius in around 20 seconds. And we also have minimal oscillations. But we then tried more testing, and when we tried the scaling parameters 7, 5, and 3, we were able to get there in around 7 to 8 seconds, and we had minimal oscillations. Cooling is much more difficult, for a few reasons. One of the reasons is we're working constantly against ambient temperature, and the Peltier is essentially trying to cool down the whole room, which is impossible. So what we needed to do is we created an enclosure for thermal isolation of the temperature control system. Additionally, heat from the bottom side diffuses into the colder side, which reduces efficiency, as well as a high temperature gradient reduces efficiency. The temperature gradient is the difference between the top side and the bottom side temperature. So to fix this problem, we attached heat sinks. So now we move to our enclosure design. We needed to cover the system. So we 3D printed this case, which simply lays on top with a simple adhesive, such as sticky thermal tape. And what this does is this ensures that not only is the system covered, but that the blood chip also has great point of contact with the Peltier. The goal of the enclosure is that we can simply put in the blood chip, have it have great contact, and then we have this indent here such that a thumb can go in with some blood, put in the blood, and then we have this Lego-like design such that we can then cover it, shown here. This improved our heating dramatically. We were able to go from 25 degrees Celsius to 37 degrees Celsius in 4 seconds. Additionally, we were able to converge to 60 degrees Celsius in 20 seconds. Additionally, once we got to that 60 degrees Celsius, we had little oscillation. So when we put it all together, we get this giant block diagram where we have the Android phone controlling the whole system through the user. The microcontroller is connected to all the inputs and outputs, the peripherals, and getting all of their data and then controlling them. So on the top left in blue, we have blood reading system where we have our Pico connected to the blood chip. And the bottom left, we have our temperature control system where this loop is in constant, this is constantly going, where we have the Peltier going to thermistor and the digital amplifier. All of this is then controlled by the PID. And then in the bottom right, we have the power system, where we have down here a charging port, where we can also change the code to the microcontroller. This charging port then also charges the LiPo battery and the phone at the same time. And we have diode protection such that we can charge the Android phone while also the phone does not provide power back to the rest of the system.
So by realize the diagram, we have our prototype board. Our prototype board is too large and too messy to cannot fit in a handheld system. So we need our PCB design. Here is our PCB revision 1, and which is 2 layers and single-sided. It is tightly designed to minimize our area, but it doesn't come with a blood reading system. And because of the COVID virus environment, the company cannot assemble the part for us. So we need to assemble the part by ourselves. Because the part is too tiny, unfortunately, our PCB board 1 doesn't work. So we have our PCB board revision 2, which is upgraded to 4 layers and double-sided board, and also come up with a blood reading system. as you guys can see, the board is even more tight design, and it comes with the blood reading system on the top. Here is our top view of the PCB design, and it is the bottom view. Here is our finalized hardware system. And right now, we just need a software interface to control the system. And we got our Android application. The Android application can communicate with the microprocessor while charging. And the microprocessor data can be changed in app by sending a JSON message. Here is our example JSON message. By sending this message to the microprocessor, it can change our hardware system to temperature control. So we can change the temperature by app. Here is our developer interface. The interface can change the parameters of the temperature control, such as set the go temp or changing the cooling or heating PIDs. Here is our scanning application. So this application, we can start scan by click the button, and we can see the status here. We can also see the temperature by the temperature plot. And you guys can see the whole process of the app by the demo video. Here is our demo video.
We're going to take you through a demo scan of our system. We're currently in the initial state of our app, but we'll take you to our developer options where we can change the variables of the microcontroller. Here, we're changing the goal temperature, and we're setting this to 32 degrees Celsius. Here's our acknowledgement back. Now what we do is we click Start Scan. From here, we insert the blood chip. Then what we do is we insert the blood, put that onto the chip, and then we cover it. Afterwards, we click Start Scan. Here, our status information turns green to show us where we're at. Then, the current temperature approaches the goal temperature. Once the current temperature is within 0.3 degrees Celsius of the goal temperature for more than a couple seconds, this starts the M-step pico scanning process that's happening right now. Now the results are ready from the pico. We now click this button, and the results are now displayed on this screen. This data now feeds into Aptitude's coagulopathy measurement engine.
We wanted to thank our sponsors, Scott Ferguson and Radhay Patel of Aptitude Inc., as well as our great professor, Professor Sukapali, the professor and Capstone chair in ECE. And then, of course, our wonderful TAs, Aditya and Kyle. And we're happy to take any questions now.
So how did you interface between your Android phone and the microcontroller? And how did you configure the host slave configuration?
To do that, we're using a USB cable, and we're splicing we're splicing the data lines and the power lines. Additionally, we have to make sure that there are resistors that are controlling essentially who is the master and who's the slave of the data. Additionally, since we're going from the microcontroller uses a different USB interface. I think it's using USB micro P, while the phone is using USB-C. We had to make sure that those things had a correct correct translation, and essentially it's just through the resistor, making sure the resistor setup was correct, as well as the transfer between those two USB systems.
Nice. And what would you say was the most challenging part of the project?
There were a lot of parts, but one head scratcher was not one head scratcher was getting all of the, one head scratcher was not understanding what a bootloader was and plugging in our finalized PCB board and not receiving any data back, and having to do essentially a lot of Googling and figuring out how to get a bootloader flashed on a microprocessor that does not have those pins mapped out. Required a lot of tricky soldering with a microscope.